Now let's go ahead and we'll look at the transistor equations, which define how this transistor is going to work. So let's say, for example, we start off with a large P well. So this whole area here is P-type, and let's say the source and the drain are both N-type. Then we'll call this an N-type transistor. So the type of the transistor depends on the doping of the source and the drain. This is the schematic diagram for the N-type transistor here. We've got the gate and we've got these two connections here, and these will be either the source or the drain. So let's say, for example, we had an N-type material. So let's say this entire region here, which is called a well, is an N-type well. Then the source and the drain are P-types. We call this a P-type transistor, and this is the schematic for the P-type transistor. It just looks like the N-type, but we've got this little circle here. Now if we had an N-type transistor, then the charge carriers here are going to be electrons. Electrons are going to travel from the source along the channel to the drain. So we would have electron flow would be the current flow. In a P-type material, the charge carriers are going to be holes. Again, the charge carrier is going to come from the source and pass through underneath the channel to the drain. In this N-type transistor, the charge carriers are electrons, and we said the electrons come from the source. Now electrons always travel from a low voltage to a high voltage, so that means that the source here, which is the source of the carriers, which are electrons, must be at a lower voltage than the drain. Now the same thing occurs, only it's the opposite way for a P-type transistor. A P-type transistor, the charge carriers come from the source, but the charge carriers are now holes, and holes travel from a high voltage to a low voltage. So in this case, for a P-type transistor, the source is the high voltage terminal and the drain is the low voltage terminal. So just to repeat, for an N-type transistor, the source is the low voltage terminal and the drain is the high voltage terminal. For a P-type transistor, the source is the high voltage terminal and the drain is the low voltage terminal. So that's something to be remembered. Now let's cover something that can sometimes cause confusion, and let's take our time to talk our way through it. Now conventional current flow is from positive to negative. Now again, this is purely a convention. So if we were to draw an arrow like this and say the current is flowing in this direction, then what we're saying is that this is the high voltage terminal and this is the low voltage terminal, because the current flows from high voltage to the low voltage. Again, this is purely a convention. So let's say, for example, we took this device here and we said that the current in this device is travelling in this direction. Now what we mean by that when we say the current is travelling in this direction, we mean the conventional current. The conventional current is travelling in this direction. But that's not how electrons flow. Electrons actually flow in the opposite direction. Electrons actually flow from the lower terminal voltage to the higher terminal voltage. So this is the actual electron flow, which is in this direction, but the conventional current is shown in this direction. That's just an anomaly of engineering, and it's cropped up historically. So let's say, for example, the conventional current is in this direction. That would mean that this terminal here must be the positive terminal, and this terminal here must be the negative terminal. So we said that this is an N-type transistor, and we said that the charge carriers are electrons, and the charge carriers come from the source to the drain. So in this case here, this end here is the low voltage, must be the source, and the high voltage side here must be the drain. So if the conventional current's in this direction, then this side here is the source, and this side here is the drain. Now let's see what happens whenever we come onto this device here. We're saying that the conventional current is in this direction. So this must be the positive terminal, and this must be the negative terminal. That is, this is the high voltage side, and this is the low voltage side. But the whole flow is in the opposite direction of the electron flow. So the whole flow is actually in this direction here. So that means that the holes flow from the positive terminal to the negative terminal. So the source of the holes is from the positive side, so this is the source, and it travels to the negative side, which is the drain. So in this device here, the source is this side and the drain is this side. So just take your time and think about that for a few minutes. This is quite important, and it can cause a lot of confusion. I'll also have a few questions that you can work your way through, which will allow you to understand this. Now we've seen how the transistor works. If we look at this one here, which is the N-type transistor, or as it's more commonly known, NMOS. So that's the N-type metal oxide semiconductor, and this one here is the P-type, so it's called PMOS, so that would be PMOS. Now in the NMOS device here, we have an electric field, so what we do is we allow the gate to rise to a certain potential, so the gate gets connected to some potential plus. And we said that the gate is a positive potential with respect to the bulk substrate, and this is the bulk connection here. So this is going to be a lower voltage than this point here. But as we said before, in this NMOS, the source is going to be the low voltage side here, and the drain will be the high voltage side. So what we do is we actually connect the bulk directly to the source, because we know that this bulk here is going to be a lower voltage than the value on the gate if the device is going to be actually carrying any current. Now what we would do, we would take this drawing here, and you could take this and put a fourth point here in that drawing, and we could take it along here and just connect it to that point there. And we could say that this here is now the new symbol for this device. But generally we don't need to do that, because it is understood that the bulk is connected to the source, so we can just leave it like this. Now the same thing goes for the P-type transistor. The bulk here is going to be connected to the source, so we would have the bulk here with a source connection. But again, we don't bother drawing that in most of the time. We can just leave it off because it's understood that the bulk is connected to the source. So we've said that this electric field that's generated between the gate and the bulk is in this direction, so from positive to negative. So it attracts the electrons up into the area just beneath the oxide layer here. Now as it attracts electrons, it expels the holes, and eventually you're going to be left with a whole load of negative ions just underneath this oxide layer, and this is going to cause our inversion. So the p-type material then looks like n-type. So we end up with a little n-type channel running from here to here, and that allows the current to then flow all the way along through the source, through the gate, and up through the channel underneath the gate, and then up through the drain. Now let's see what happens whenever we change the gate voltage with respect to the bulk. So we could write the voltage GB, so that's the voltage from gate to bulk, and the bulk is just the substrate here. If we were to draw this in, it would just be a p-type substrate. But we've said that the bulk is in effect the same as the source, so the bulk connection here is sitting at the same potential as the source. Okay, so that just sits at exactly the same potential, so in effect it's, as far as the voltage is concerned, it's just the same point. So rather than writing voltage between the gate and the bulk, we could just start writing voltage between the gate and the source. And this is what we'll use from now on, VGS. But remember that the VGS, that is the gate to the source, is the same as the gate to a bulk here, which is just the p-type substrate. So if the voltage between the gate and the source is negative, then in effect we're saying that the gate voltage is less than the source voltage, or equivalently the gate voltage is less than the bulk voltage. That would mean that the electric field here, instead of going from a positive down to a negative, would be going the opposite direction. It would be going from the positive here up towards this negative. So that would mean that we would be attracting lots of holes into the channel here. So it means that the concentration of the holes in the channel would be greater than the concentration of the holes in the bulk as a whole. This is called accumulation. So in effect, we're turning the device off, or you could say we're turning it hard off. Now let's say we were to raise the gate voltage up. There would become a certain point at which the distribution or the density of the majority carriers, in this case in this substrate, which are holes, is the same as the density over the entire bulk. And that point there, we call that point the depletion. Now if we were to raise the voltage on the gate until it was positive with respect to the source, then at that point the charge carriers, the holes, would be ejected and electrons would be attracted up into this region. And at that point we would have our inversion, and that's when the N channel would appear here. And that would allow current to flow from the source to the drain. So we've got these three possibilities: accumulation, depletion and inversion. Now there's a certain voltage at which each of these occur, or the transition between each of them occur. Now between accumulation and depletion we have the flat band voltage. Between depletion and inversion we have the threshold voltage. Now the one that we are interested in and we'll be dealing with through the rest of this course is the threshold voltage. So this is the voltage at which the channel just starts to conduct. That is, we just start to get inversion. Now we know that this device works by applying a voltage to the gate, and this gate voltage controls the current through the device. So it's going to be a voltage controlled current source. Now we want to create equations that relate the voltages and currents in this device. So we're going to start off by using a little bit of common sense. We know that when the gate voltage here is high enough, we get an inversion, and this creates a little N-type layer that allows current to flow through this device. Now, if the inversion is very, very small, meaning that if we have a very, very narrow channel generated here, so there's a very narrow little inversion channel, then we're not going to have a lot of current flowing through because the channel is very, very narrow. If the channel was a lot wider, so let's say the channel was that width, and we had all this area available to us, then we would have a lot more current flowing through because the inversion layer depth is larger. So we've got a much larger or deeper inversion layer, which allows a lot more current to flow. So what controls the depth of this inversion layer? Well, we've almost answered this question already. We know that we don't get inversion unless the threshold voltage has been reached. So let's say the threshold voltage, for example, is 1 volt. So this means that if we were to look at the voltage between the gate and the substrate, so there's a substrate there, so in effect the substrate there is equivalently the bulk. It's the same thing, the bulk connection and the substrate connection. So if the voltage between the gate and the substrate is greater than the threshold voltage, then we're going to get inversion. So let's say, for example, we actually had the VG minus V sub, and let's say it equaled VT, then inversion is just starting. But let's say we made that VG minus V sub greater than VT, then we're going to get inversion. If we made it a lot greater than VT, we're going to get a lot greater inversion. So the inversion layer depth has got to be directly proportional to this VG minus the V sub. Okay, and that's what we've written here. Inversion layer depth is directly proportional to VG minus V sub. As VG minus V sub goes up, the inversion layer depth goes up. But we can rewrite this equation here again as VG minus V sub. And notice that VT is a fixed value, it's just a number. So we could say that this here, and we could bring it over to the other side, we could have a minus VT. So we know the inversion layer depth is directly proportional to this. If it's directly proportional to this, it's still just directly proportional to this minus this constant VT. So we can say, finally, that inversion layer depth is directly proportional to VG minus V sub minus VT. So this is the start of our hunt for the current and voltage equations. Now that's the video going on for nearly 20 minutes now, so I think there's enough in this one video. We'll continue this on the next video where we finish off working out the current and voltage relationships for our MOSFET. So thank you for listening, I'll get you in the next video. Goodbye.